Hello, this is the third and last video of the module Polarization Optics for the course ECE 513 Intro to Optics and Photonics. Today's class is about defining Jones vectors and their matrices. We're going to derive the polarization state of an output beam of light after passing a cascade of polarizing elements. So the elements are going to be defined by the Jones matrix. And we're going to understand how the reflected and refracted ray is going to change the amount based on the polarization state. So we were saying the other two classes that the polarization is related with the change between the components of the electric field, and we can write our electric field in Cartesian coordinates. So we know here that every coordinate is going to have an initial amplitude with the corresponding delay, and we're going to have exactly the same for the y component. And the Jones vector idea is that we're going to write these two components in terms of a vector. Sorry, this last one is with respect to the y. So this is our Jones vector. So let's assume that we have horizontal linear polarization state. So that means that we only have our x components. So the electric field is given by a 0x with its corresponding phase, but the y component is 0. And now when we normalize it, so this is going to be normalization. The horizontal linear polarized state, that's going to be 1, 0. Similarly, we can have our vertical linear polarized light. So that's going to only have, it's going to be completely orthogonal. So we only have our y component. So our electric field is going to be 0, and then the y component, when we are considering its absolute value, its amplitude, and the phase. And again, if we normalize it, now the Jones vector for vertically linear polarized light is going to be 0, 1. The other case is when we have linear polarized light, but it's oriented by 45 degrees. So that means that my x component and my y components are exactly the same. So I can take the x component outside as a common factor, and then here we're going to have 1, 1. And when we normalize, then our 45 degree linear polarized light, that's going to be 1 over a square root of 2, 1, 1. So yes, I think this is clear, but this, sorry, I meant to. So this square root of 2, this is the normalization, is going to be the norm. So this is going to be when we do the absolute module square of the x and y component, and then the square root. So that's how that one is estimated. The final cases that I want to discuss about the Jones vector is when we have right hand circular polarization. So that means that the amplitudes, the initial amplitudes, are gonna be the same, but now our phase of the y component leads the phase of the x component by 90 degrees. So that means that our electric field is gonna be, we say that we have originally the same phase, phi x j, and here it's gonna be the phase of the x component minus 90 degrees in radians. We can definitely take outside the phase as a common factor. So here we have 1, the exponential of minus j, minus j pi over 2. So our electric field is gonna be and then this is gonna become minus j if we apply Euler. And now when we normalize, our right hand circular polarized line is going to be 1 over a square root of 2, 1 minus j. We can do the same if we have left hand circular polarized line. So again, the initial amplitudes of the x and y components are the same. By now the phase of the y component lags the phase of the x by pi over 2. So kind of going, if we take the x component as a factor, here we're going to have 1 and then the exponential of j pi over 2. So this is going to be the common factor 1j. So when we normalize the Jones vector for the left hand circular polarized line, 1j. Let me try to make sure that you guys understand that what is on the denominator is the square root of 2. Alright, so I want to talk a couple of insights of Jones vector. So the first insight is like, let's consider the superposition of coherent beings. In this case it's going to be 2 coherent beings whose polarization state is going to be right hand circular polarized, and then the other one is going to be left hand circular polarized. And now what we need to know is, like, we need to kind of figure out what is going to be the resultant polarization state. This is what we are now discussing. Alright, so the first thing that I want to show is, like, we know that they are saying that they are coherent, right? So what is the meaning of coherent? So this is gonna be going back to module 2. But coherent means that the phase difference it's independent of the time so that means that the phase difference remains invariant or remains constant. The other thing means that our beams needs to be monochromatic. Otherwise, we cannot do it. So we know that we have two beams that they are coherent. So that means that we can sum the Jones vectors of both of them. And in this particular case, we know exactly where are the Jones vectors, right? They are exactly the same. Just the difference is on the sign with respect to the y component. When we sum them, we're gonna have 2, 0. So we see here that we don't have y component, and that means that we're gonna have a horizontal linear polarized light. So the light is gonna be horizontally polarized. The second insight is like, let's consider that we have two beams that are represented by a Jones vector. Each of the beings, and then here instead of R is gonna be is represented by a Jones vector, right? So that means that we have here, we have E1, and then we have the other vector E2. So we know that we're gonna say that these beings have orthogonal polarization states. So for example, let's assume that we have horizontally linear polarized and then vertically linear polarized, right? The difference between them is it's a rotation of 90 degrees. If the scalar product of the first vector with respect to the second one conjugated, that's gonna be equal to 0. So we can, and I'm gonna try to use here colors now because I feel that's gonna be a little better. So let's assume that here we have E2, and now here I have E2 conjugated. So if we want to express the component of the first beam x is gonna be multiplied with the component of the x, but we're gonna have their conjugated, and we're gonna have exactly the same for the y. So this is gonna be the second y conjugated. So when the scalar product between the Jones vector and the conjugated of the second beam is 0, then that means that it's gonna be the polarization states are orthogonal. On the multi-choice questions, we have one problem about this, and there is a video. So feel free to go there and watch that video. You have more questions. So this is just kind of like a summary of what we were saying when it's horizontal, vertical, right hand, circular polarization. Just, like that's gonna be circular polarization left hand, or right hand circular polarization, or left hand circular polarization. This is just a general. This right here is gonna be completely a general case where it's linear polarization, but instead of having 0, 90 degrees, it's arbitrary. So how we can write it down? So we use the Jones vector to characterize the polarization state of a beam of light, but then we're gonna use the Jones matrix to characterize the polarizing elements. So every element is gonna be associated with a Jones matrix. And we have the horizontal linear polarization. If we have the vertical, we're just gonna put 0 in the first element, and then we're going to have in t22 equal to 1. The wave retarder, remember, those are a full wave plate, half wave plate, or quarter wave plates, and what is going to happen is just the last element, the t22 element, is the one that is going to change based on how much we are delaying one of the components with respect to the other. And then the polarization rotator is just if one of the components we want to rotate. But if we want to kind of like break down, what we're gonna have is like at the output, we're gonna have the x component is gonna be related with the first row of the Jones matrix with our Jones vector of the input component, and then the y component of the output is gonna be with the just multiplication of a matrix with an array, something that you should be already familiar with it. But as you can see, in a more general case, the two components, the x and y component of the output, are going to be related in general with the x and y components of the input. So let's do a couple of short problems. So right now here we know that we have linear polarized light at 45 degrees. So that means that if you remember what we did it before was 1 square root of 1 1. And this is going through a quarter wave plane. So the quarter wave plane, let me try to use here another one. So the t of the quarter wave plane, the t of any retarder is 1 0 0, the exponential of minus j, capital phi, but now that phi value is gonna be 90 degrees for a quarter wave plane. So that means here that we're gonna have 1 0 0, the exponential of minus j pi over 2, and then if we apply Euler, we're gonna see that this is 1 0 0 minus j. So now we want to know what is gonna be the output after the quarter wave plane, right? And we know that we're gonna have here our quarter wave plane it's gonna be our quarter wave plane. Now multiply with our input, with this graph a Jones vector of 1 over a square root of 2 1 1. And when we do this, it's gonna become 1 over the square root of 1 minus j, sorry. So this 1 over minus j, if you kind of scroll down a little bit, you're gonna see that that's the right hand circular polarization. So we have changed linear polarized light at 45 degrees into circular right hand circular polarization just using a quarter wave plane. So the second example is still we have linear polarized light at 45 degrees, but now we are replacing the quarter wave plane to a half wave plane. So again, the half wave plane, it's a retarder where we are delaying one of the components by pi. So when we have the exponential of minus j pi, again we apply Euler, so we're gonna see that this is gonna become minus 1. So what we're gonna have at the output is 1 0 0 minus 1, and that's gonna multiply our input Jones vector, and then here we're gonna have 1 over a square root of 2, and then it's gonna be 1 minus 1. So what we are having here, if you cannot see, the only difference is our x component that is flipped. So that is gonna be circular light, but now it's gonna be oriented or rotated at minus 45 degrees. Alright, so the third example short problem is that we have left hand circular polarized light. So if you go a couple of slides, you're gonna see that the left hand is 1 over square root of 2 1 minus j, and now it's going to our quarter wave plate. So our quarter wave plate, the Jones metric is 1 0 0 minus j, and our input is left hand circular polarized light 1 minus j. So our output here is gonna be 1 square root of 2 1 j square, but j square is gonna be minus 1. So here what we're gonna have linear circular light oriented at minus 45 degrees. The final example is when we have a halfway plate and it's illuminated by a right-hand circularly polarized light. So this is the case, like if you remember a halfway plate, we're going to introduce a phase of pi or 180 degrees. So our right-hand circularly polarized light is going to become a left-hand circular polarized light. So we know how the Jones vector is gonna change when some input vector is gonna travel with a polarizing matrix, right? We know that we're gonna have like the output is gonna be given by the multiplication of the Jones matrix with the Jones vector. But let's consider now that we are rotating our input vector, and this is gonna be rotate the polarization state. So now my new input is gonna be the rotated version of my original input. And now we are considering that my new output, that's also gonna be the rotated version of my previous output. So we know here that we have our rotating matrix, but the output, we know already that the output was A with my original input vector, and now I can put here an identity matrix. So that's gonna be the inverse of the rotation matrix with the rotation. So this is gonna be my identity matrix. So if I put it there, what we're gonna have is our rotation matrix, the matrix of our element, the inverse of the rotation matrix, and now here we have the rotation matrix with our original input. But this is what we say is gonna be our rotated input, right? So at the end of the day, if you can see, we're gonna have like our rotated output is gonna be our matrix, our Jones matrix, sandwiched by the rotation, the multiplication of the rotation matrix, and then here we're gonna have our kind of like our rotating input. But this, and I kind of don't have a lot of colors anymore, but this is right, this is kind of like my new, or the rotation of the Jones matrix of the element. So for example, let's consider here that we have a horizontal linear polarizer. So we know already that it's going to be 1, 0, 0, 0. And now we want to rotate it by an angle that is going to be arbitrary, and it's going to be theta. So here we have our rotation matrix. This is going to be A, and then the inverse. And then when we estimate this is going to be cosine square, cosine sine, again here cosine sine, and sine square. And if we particularize for the angle that we have 45 degrees, now our new matrix, that's gonna be 1.5, 1.5, 1.5, and 1.5. Why? Because the sines and cosines are the same value. Also, I want to see like if the angle that we are rotating is really small, that means that the cosines are gonna be practically 1, and when we have sines we're gonna put just the value. Then for this particular case, the rotating Jones matrix, that's gonna be 1 theta theta 0. So those are kind of particular cases of how to rotate a horizontal linear polarizer. So in general, what you have on the system, it's more than one polarizing element. So what you need to do, you need to apply the cascade. They're gonna go one element after the other. So what is important here, and this is kind of like what we did on the ABC matrix, the order matters. So we always need to kind of put the last elements on the beginning, and then excuse me, the first elements that the light is seeing on the matrix is going as the last one when we do the multiplication of the matrices. But remember, the order matters, because you're gonna get completely different results. So let's do this this short example where we have 3 different elements. The first one is a linear polarizer oriented around the x component, so it's the horizontal, so that means that it's gonna be 1, 0, 0, 0. The second component, T2, this is gonna be a linear polarizer oriented at 45 degrees. So we already did that one, is 1 over 2, 1 over 2, 1 over 2. And then the third component is gonna be a linear polarizer oriented along the x direction, the y direction. So that's gonna be 0, 0, 0, 1. So we're gonna have T3 multiplied by T2 multiplied by T1. Now here we're gonna have 0, 0, 0, 1, 1.5, oops, not the same color, 1.5, 1.5, 1.5, 1.5, and finally 1, 0, 0, 0. So the result is gonna be 0, 0, 1 over 2, 0. So this is our corresponding, this is the kind of like the effective Jones matrix. So now our output is gonna be our effective Jones matrix multiplied by our input. And a priori, we don't know anything of our input, so we're just gonna leave it with its x component and the y component. Now we're gonna see that the effective Jones matrix is just gonna only have the output, only gonna have one component, so no x component. So that's gonna be like vertical linearly polarized. BLP. So that's how it's gonna be the polarization state of the output electric field. The other example is now, and this is kind of to show that the order matters. We have two different scenarios. We have two quarter wave plates that they are placed in cascade, but in the first option they have the fast axes are parallel. So let's assume, for example, that we have two quarter wave where the fast axis is the x-axis, but they have parallel, so they are exactly the same. So the output is going to be 1, 0, 0. Here you have j minus 1, but remember that j minus 1 is going to be minus 1. So this is like, if we write this minus 1 as a j exponential of minus j phi, this is gonna be like our phase is gonna be pi. So this is acting as a half wave plane. But on the other scenario, when the two quarter wave plates are orthogonal, so that means that one of them is oriented along the x-axis, but the other one is gonna be along the y-axis. Now here the solution is 1, 0, 0, 1. So this is my identity matrix. So that means that we have here a full wave plane. So our phase introduced is gonna be 2 pi. So the polarization state remains the same. Alright, so this is kind of like, I want you to think about this as kind of like some kind of modification Snell law. So we know that we have an interface, right? And we have here our refractive index at 1, and then we are meeting some interface that is going to be some refractive index. And the Snell law tells us that the reflected angle is always the same as the incident one, but the refracted one is going to depend on the relationship of your refractive index and the angle of the incident line. The question now is that in a general case, we have the incident line is polarized, but let's assume that in general we consider that it's unpolarized, right? So we have the same amount of component in the two orthogonal perspective. One that is going to be parallel to the surface, and the other one is going to be perpendicular to the surface. So in general, the amount of light is going to change based on their orientation, if it's parallel or vertical, and it's going to depend on the relationship of the angle. But in general, the amount of light that is reflected and transmitted, we always need to obey the principle of energies. So for the same polarization state needs to be equal to 1, but the sum needs to be equal to 1, but how much it is going to depend on your incident angle and then the refractive index. It's going to be a particular case where it's going to be the incident angle is going to be equal to the Brewster angle. So the Brewster angle is such where the angle between the reflected and the refracted is 90 degrees. So this is going to be 90 degrees. So at the end, the angle is going to be estimated as the inverse of the tangent of N2 versus N1. So definitely the angle N2 needs to be higher than N1. This is a condition. Otherwise, we cannot have the angle of 90 degrees between the refracted and reflected beams. What is really important about for the Brewster angle is that the reflected ray is completely polarized, where the refracted one is slightly polarized. And it's just for this particular angle where we're gonna have this condition. So this is what I wanted to talk to you in this last video of Model 6. And those are some external resources that I have found really useful across the different years that I have been teaching the course material, and I thought that it's great if you can have access to them and also watch them and find if you think the same like me. That's everything for today. Thank you.